It is a third and final part of my 3-part tutorial explaining how to use my free program for calculation of surface plasmon. What is the reason why we are able to reduce the plasmonic loss to such a small value? To understand the reason, let us calculate these figures and distribution of optical field across the thickness of double-dielectric plasmonic structure. Let me reduce number of calculating points of scan to 10. Calculate scan and calculate the optical field for each point of scan. Let us take a look at the field distribution across the thickness. There is a spark of intensity of optical field inside silicon dioxide layer. The optical field decays in both dielectric and metal layers. Please take a close look at the rate of decay of the optical field in dielectric and metal layers. As we approach the cutoff thickness of 9 nanometers, the optical field penetrates deeper and deeper inside of the dielectric. In contrast, the penetration of optical field in the metal remains the same. As a result, the percentage of optical field inside dielectric increases and correspondingly the percentage inside the metal decreasing. Example, that is a thinner silicon dioxide, and we go Let us calculate the dependence of penetration depth on the silicon dioxide thickness. For this purpose, let us increase the number of points for the scan calculation against 200. And again, we need to recalculate field scan for each point. So shifting to the left part of calculations, and let's choose the skin depth in down dielectric and calculate. As you can see, the penetration depth sharply increases as silicon dioxide thickness approaches to the cutoff thickness of 9 nanometers. In contrast, the penetration depth or the skin depth in metal remained practically unchanged, around 51 nanometer. Therefore, the optical field is pushed out from the metal to the dielectric as silicon dioxide thickness approaches to the cutoff. Percentage of optical field in dielectric increases, and correspondingly percentage of optical field in metal decreases. Since the metal is responsible for the absorption of surface plasmon, the propagation loss of surface plasmon decreases near the cutoff thickness. Just copy this data, paste to origin, it's for chromium, and let's choose like a cobalt. Yeah, little bit reduce here and 0 layer. The cobalt here, cobalt. We can calculate calculate. No, let's. Yeah, cutoff is near 6.5, so let's put 6.8. Yeah, more point. Don't forget to recalculate field for each point of scan. Yeah, you see, I have a warning. So now calculate. So it is for cobalt. And we just plot it. So you see we got the same graph. The reason why the penetration depth in dielectric increases when silicon dioxide thickness approaches the cutoff thickness is because the confinement of optical plasmon to the metal surface becomes weaker. However, you should not worry about this. The optical confinement of a surface plasmon is so strong that even with a substantial reduction, the plasmon confinement is still larger than, for example, the optical confinement of waveguide mode. It is not necessary to worry about plasmon confinement in realistic plasmonic device. It is always sufficiently strong. When silicon dioxide thickness is thicker than cutoff thickness, the confinement at the metal interface is not sufficient to support the propagation of surface plasmon, and there is no surface plasmon in such a structure. For example, case of 7 nanometers of silicon dioxide thickness, there are no any surface plasmons. I hope you understand the simple magic for reduction of the propagation loss of a surface plasmon. I just repeat the important steps which should be taken. It is important to use a thin insertion layer or smaller refractive index near interface. It is critically important to find a very specific thickness of this layer at which the surface plasmon is close to the cutoff conditions and at which the optical confinement of surface plasmon is weakened. I would like to emphasize that this simple method is very important and unavoidable magic for plasmonic technology when you would like to fabricate a practical and competitive plasmonic device with a small insertion loss. In a realistic fabrication technology, it's not always easy to find the cutoff thickness. The interface roughness, material interdiffusion near interface, and the inhomogeneity of the thickness of the insertion layer all influence strongly the cutoff thickness. Often it's necessary to find the cutoff thickness experimentally by a calibration. The general rule is that a surface plasmon likes a sharp and smooth interface very much. Therefore, perfection of the fabrication technology is critically important for a surface plasmon. I have used this technology with different plasmonic structures for many years. It is not always simple technology, but it is always very effective technology. Finally, I would like to show that the cutoff thickness for surface plasmon, case of thin insertion layer, is not only one cutoff thickness. There is another cutoff thickness for a thicker silicon dioxide layer. Let me increase the silicon dioxide thickness up to, say, 1500 nanometers. When silicon dioxide layer is thin, most of the optical field of surface plasmon is inside of silicon here. Therefore, effective refractive index of plasmon is close to the refractive index of silicon. When the silicon dioxide layer is very thick, the silicon is very far from the metal interface. Most of optical field of surface plasmon is inside of silicon dioxide, and therefore the effective refractive index of plasmon should be close to the refractive index of silicon dioxide. Therefore, as suggestion, let's use the refractive index of silicon dioxide, which is just first layer close to interface. So you see. Next, let's try to calculate. You see, the program cannot find surface plasmon. As you remember, effective refractive index of surface plasmon is slightly larger than effective refractive index of dielectric. So let's a little bit increase suggested effective refractive index. And now you see no problem, program can find the surface plasmon. Next, let's scan down thickness of silicon dioxide from this very thick value, large value, to smaller value and see is there any cutoff thickness. For this purpose, let's start scan from this thickness, for which we already calculated effective refractive index of plasmon, and we're going down to very small thickness, so we can increase number of points. As I have told you, for this first calculated scan point, the program will use this value as suggested value. For each next point, the already calculated value of the preceding point is used as suggested point. When there are more steps and points are closer to each other, the probability to find a solution is higher. Let us calculate the scan. You see, again we found some critical thickness of about 850 nanometers, and you can see the losses steadily decrease when the thickness of silicon dioxide layer decreasing. We can find the cutoff thickness even more precisely if, for example, we will start from thickness of 1400 nanometers, for example. We put like this, and we use as suggestion. We will use data exactly calculated already for this point. So just put this here, and a suggestion we use from scan. You see we got these numbers, and also it's not necessary to go so much down. We can stop at 800. Push calculate scan. So you see we can even more closely approach to the cutoff thickness from even smaller loss. As you may recall, in structure with the same silicon dioxide layer, the surface plasmon are supported when silicon dioxide layer is thinner than cutoff thickness. In contrast, this structure with thick silicon dioxide layer supports the surface plasmon only when silicon dioxide layer is thicker than cutoff thickness. The plasmonic structure with a thicker cutoff thickness also can be used as a structure for low propagation loss plasmon. However, from my experience, the structure with a thinner cutoff thickness is easier to optimize and therefore preferable. I hope you will find my program useful and easy to use. I hope the program will help you to fabricate competitive plasmonic devices with a small loss and excellent performance. Thank you very much.